Okay, so in this video I would like to look at some other examples of line integrals. In the previous video we calculated the line integral for a special force. Now we're going to do for a specific force. Now we're going to do it for another certain force and another path. Okay, and this time, so this time we're not going to use parameterization. We're going to use a different approach. So new example 2. So example 2, whoops, zoom in. Okay, so example 2. So we consider the force F, okay, this force right here, which is equal to a constant, times x, y, I direction, plus y squared j direction. And we also consider the path along which this force acts upon. So this path is simply the so C. Okay, so C is going to be the path. Firstly, it's going to be made up by two lines. Firstly, from the point 0, 0 to the point 0, 1, and then from the point 0, 1 to the point 1, 1. Okay. So in this case, parameterization could actually be done. We could parameterize the line, but there's a faster way. Usually when you have these lines, it's easier to just keep x and y, and we'll see why right now. So let's calculate into the work. The work done is equal to the integral, so it's going to be equal to the integral along the path C of the force F dot product dr. Okay, dr is related to the path we chose, and we can actually split it into two parts. Okay, we can split it into the work done by moving it in this first path, which I'll call path A. So the work done in moving it along the path A of f of A dot product dr, plus the same thing, so the work done by moving it along the path B. Okay, so we divided our line integral into two smaller line integrals. Okay, so let's just draw another diagram to have an idea of what's going on. So we have our two axes right here. Okay, let's say that this point right here is, oops, let's say that this point right here is 0, 1. Okay, so it's going to move along this line right here initially. Okay, and this is going to be path A. Then it's going to move up. Okay, it's going to move to the point 1, 1, and that is our path B. Okay, so this is path B. And so let's just calculate the line integral separately. So in this first case, what is the line integral equal to? It is A of, what is the force in this case? Well, here notice that along the path A, x is variable. However, y is always equal to 0, right? Because this is y-axis, z-axis, x-axis, so y is equal to 0, which means that the force is constantly 0 because in both cases it is dependent on y, right? Here y is equal to 0, so the I component drops, and the same goes for the j component. So here we're going to have 0 as our force, so obviously this line integral is just going to be null. Plus line integral b. Okay, so what about the path b? In the path b, we have that x is constant, it's equal to 1, and y is variable. Okay. What does this mean? This means that our force is not null. Okay. Our force is equal to a. xy is just going to be y, I direction, plus y squared, j. Finally, in our line integral, we also have dr. Okay, that's the infinitesimal line path. And dr, well, it's just going to be dy, right? Because we're only moving in the y direction. We're going to move in this up direction. dy j. Whereas here it was dxi. So dr is equal to dy j. And so finally we can evaluate the integral. So we said that the force is equal to a yi plus y squared j dot product dyj. Okay, and let's evaluate the dot product. So the I component is just going to drop, right? Because in the dr term, in the dr vector, we don't have an I component, so it's going to drop off. Instead, the j component is going to remain, obviously, so we end up with the integral of y squared dy. And what does y go from? It goes from 0 to 1, and those are our limits of integration. So the integral from 0 to 1 of ay squared dy. And this is just your standard integral, and you end up with, I believe, a thirds. Yeah. So a over 3, and that is your final answer. Now I'd like to kind of mix things up. I'll actually add another path, and I'll call it C. No, I'll not call it, I won't call it C, I will call it S. Okay, so S is going to be the path from 0, 0 to 1, 1. It's going to be the direct path, so it's going to be this line right here. Okay, this path right here is S, whereas the blue path that I drew before was C. Okay, and how do things change? The force is going to remain equal. I want to see if the work done is going to be the same, is it going to be less? First of all, just make a prediction. Do you think it's going to be greater or smaller? Okay, so let's do the same thing. In this case, you could parameterize the line, but I'm just going to use the same approach. Okay, so what do we end up with? So the work, again, equal to the line integral along the path S of f dot product dr. Okay. Now, how can we define dr? In this case, dr is equal to, well, think about the slope of the line, right? This line has slope 1, which means that for every small step that we make in the I direction, we're going to make that same small step in the j direction. So this is equal to dx I plus dy j. Okay, and we plug this into our line integral. So the work is equal to line integral along, actually it's not going to be along the path S anymore, of the force, which is a xy I plus y squared j times dx I plus dy j. Alright, but just leaving it like this won't work, because if you just calculate integral like this, you find that you end up with variables and not with actual numbers. And that is because we left this as an expression of two different variables. Instead, we could have simply written dx, right, I plus j, because the step that we're making to the left is equal to the step that we're making to the right. The slope is 1, right? For a small step dx in the I direction, we have the same small step in the j direction. And we just apply that. So using this fact, we get that this is equal to the line integral of, well, y is simply going to be equal to x at this point, right? This is the line y equals x, so we get a x squared plus I direction, plus again x squared j dot product dx I plus j. Okay, and we evaluate the dot product. This is simply equal to a times 2x squared dx. That's nice. And what does x go from? It goes from 0 to 1. And in the end, we get that this is equal to the integral 2/3 of a. Okay, so 2a thirds. So we notice that the work done in this case is greater. Okay, so if I call this ys and this yc, then we notice that yc is smaller than ys. This is a very interesting result, because even though we took a direct path, it turns out that the force components are actually greater. So in the end, we have to apply the work done is greater. So even if we took a longer path in C, maybe the force components were not exactly tangent, so the components were smaller, and therefore the final work was also smaller. So hopefully that helped with a bit of the calculations. Maybe if you don't parameterize the curve, in certain cases that could work, such as in this case.